Hello everyone. Let me start with a simple question. Have you ever tried sliding down a playground slide and noticed that you move slower than if you simply jumped off from the same height? That's the magic of physics at work on an inclined plane. When an object moves on a smooth incline, it doesn't accelerate with the full force of gravity. Instead, only a part of gravity pulls it down along the slope. This part is written as g sine theta, where theta is the angle of the incline. Perpendicular to the slope, gravity is cancelled by the normal force. That's why the motion we study is purely along the slope. As you can see in the diagram, the weight splits into two components, g cos theta balancing the normal and g sine theta driving the motion. This simple but powerful idea leads us to new equations of motion. Now let's move to the first equation of motion. You already know the general form, v equals u plus at. On the inclined plane, acceleration is replaced by g sine theta. So the equation becomes v equals u plus open bracket g sine theta close bracket into t. Here, u is the initial velocity, v is the velocity after time t, and g sine theta acts as the effective acceleration. If the body starts from rest, u equals 0 and velocity simply increases directly with time and the steepness of the slope. Next, let's derive the second equation. Normally, we write displacement s as s equals ut plus 1 by 2 a t squared. Again, replace a with g sine theta. The result is s equals ut plus 1 by 2 into open bracket g sine theta close bracket into t squared. This gives the distance travelled by the body along the slope. Notice the shape of the graph here. Displacement increases quadratically with time, forming a smooth upward curve. That's because of the uniform acceleration acting along the incline.
Now, for the third equation, recall the standard form v squared equals u squared plus 2as. On the incline, this becomes v squared equals u squared plus 2 into open bracket g sine theta close bracket into s. What's special here? This equation does not involve time. It directly connects velocity with the displacement covered. This is very useful in solving problems where you are given distance, but not the time taken. Now let's think about motion in the opposite direction. What happens when a body moves up the incline? Here, the acceleration works against the motion. So instead of g sine theta, we have negative g sine theta. That changes our equations. V equals u minus g sine theta into t, s equals ut minus 1 by 2 into open bracket. G sine theta close bracket into t squared, and v squared equals u squared minus 2 into g sine theta into s. This means the object slows down or decelerates until it comes to rest at the maximum point before sliding back down. As you can see in the diagram, upward motion is always accompanied by retardation. Let's apply these equations to a numerical problem. Example, a body is projected up a smooth inclined plane with initial velocity u equal to 10 meters per second and theta equal to 30 degrees. Find the time of ascent, maximum distance traveled, and velocity after 4 seconds if it slides back down. Step 1. Effective acceleration. Ichakpan g sine theta 9.8 into 0.5, 4.9 meters per second squared. Step 2. While moving up, acceleration is negative. Time to stop for u divided by g sine theta, 10 divided by 4.9, approximately 2.04 seconds. Step 3. Maximum distance traveled, log u squared divided by 2g sine theta, or 100 divided by 9.8, 10.2 meters. Step 4. After sliding back for 4 seconds, velocity over 0 plus 4.9 into 4, 19.6 meters per second. This example shows how equations on an incline can handle both upward and downward motion seamlessly. Let's quickly recap what we've learned. On a smooth inclined plane, the effective acceleration is always g sine theta. The three equations of motion adapt beautifully by replacing acceleration with g sine theta. For downward motion, velocity and distance increase under g sine theta. For upward motion, deceleration occurs due to negative g sine theta until the body comes to rest. Key relations are v equals u plus or minus g sine theta into t, s equals ut plus or minus 1 by 2g, sine theta into t squared, and v squared equals u squared plus or minus 2g sine theta into s. These principles are not just abstract. They explain the motion of vehicles on hilly roads, the design of ramps, and even roller coasters. I hope you now have a clearer picture of how inclined planes change the rules of motion. See you in the next session with another fascinating concept of physics.